can get started. Before we begin, any questions from the previous materials? So now today we are going into actually using the vectors that we've prepared so far, or the training samples, to train a classical model and the neural network model. So before that, any question? I think I've seen one question on ClassSum, which was about the HADMID. Is the student who asked the question or posted the question on ClassSum here today? 그 클래스홈에 질문하신 분 오늘 계신가요? 아, 네, 최우성님이신가 보네. 혹시 해결되셨나요? 아니면은 여전히 뭐 문제가 있으신 건가요? 그게 HADMID가 안 맞는 게 있다는 건 거죠? 네. 근데 뭐 그럴 수도 있어요. 이게 뭐 그 어드미션에 있는 HADMID랑 그 다음에 이제 뭐 다이그노시스나 아니면은 뭐 프리스크립션 쪽이 아니 프리스크립션이 아니라 그 프로시저 쪽에 있는 HADMID랑 100% 막 다 뭐 맞는 거라는 보장은 없거든요, 사실. 그래서 그런 거는 그냥 예외 처리해가지고 빼내셔도 상관은 없습니다. 근데 저도 뭐 실제로 그런 게 있는지는 저도 뭐 워낙 이제 오래돼가지고 기억이 뭐 가물가물한데 하여튼 뭐 100% 다 맞다는 보장은 없습니다. 데이터 특성상. 네, 뭐 한 번 더 시도해 보시고 혹시 해결되셨으면은 클래스룸에 다시 올려주시면 감사하겠습니다. 네. 네. All right, so that's that, and so just a quick recap. So last time what we did was we went through the MapReduce. We're not going to go through the MapReduce again. So we talked about the MapReduce and then the common prep. So before we actually train a model, we talked about common preparation, which is splitting the data into train, valid, test set, and then creating a string to integer mapping for features that have string values. So these were the string valued features, so they become categorical. And of course, these are multi-label string values again, so they also become categorical. They also need to be mapped to an integer, and then this would be the example where the string values like this are all mapped to their individual vocab or integer values, which are the same thing. List as well, so or for ND5W vancomycin, they also all need to be mapped to an integer, and then this is what you get after the integer mapping, and then you need to actually vectorize the features so that you can actually form a really long vector, which are, in our case, about 40,000 dimensional vector. So this vector represents this feature, this information here, which is a single hospital admission, which consists of like various information: admission type, marital status, ethnicity, gender, admission reason, and then the diagnosis list, medication list, and procedure list. So if you all convert them into a vector and then concatenate them, then you get this. You can see that like there are 3 admission types, 5 marital status types, 4 ethnicity types. Gender is binary, so there's only one dimension here. So on and so forth. So about 40,000 dimensional. And please keep this in mind because we're going to reuse this data structure, this vector, over and over again for the logistic regression example and the neural network example. So that's the vectorization. And we also talked about what to do when you have duplicate features, such as like when you want to represent an ICU admission, a single ICU admission into a vector form, and you have duplicate information for such as taking body temperatures multiple times or taking blood pressures multiple times, then you need to either handle this using by averaging the values, all the body temperature values or all the blood pressure values. You can average them, you can take the minimum, you can take the maximum, you can actually sum them up, or you can actually use all of them. You can take average, min, and max, so that each dimension or each feature becomes a three-dimensional vector. So one dimension responsible for average, another dedicated for minimum, and the last dimension dedicated for maximum. So that's up to you. So how you would vectorize the features is a design choice. And lastly, if you have multiple representation vectors, so this is if you remember, the blue strips are single hospital admissions, and this patient, for example, went to the hospital 3 times in their lifetime, and each hospital admission becomes a 40,000 dimensional vector. And suppose that you want to aggregate them to obtain a patient representation vector, then you would have to, again, it's a design choice, but you can either average them, or you can sum them, or you can put them into RNN, or whatever you do, the end goal is to obtain a fixed size vector, so that then you can push that vector into a model again to make a prediction. So that's what we talked about last time. So once we have the vectors, now we can actually train the prediction model. And today we're gonna go through the classical model first, and then hopefully, if we have time, we can cover the neural network example. So there are a lot of, so before the era of deep learning, or the introduction of deep learning, a lot of model has been proposed in the machine learning community, and we're not going to go through all of them, but typically these are like the typical classifier models that you can use for classification or prediction. And out of this, we're gonna look at the logistic regression. Oh, actually, I need to. Yeah, sorry about that. So yeah, out of all the classical models, we're gonna take a look at the logistic regression, which is probably the most popular model in medical studies. Or maybe all statistical studies. If you have a fixed size vectorized data sample, and you have an outcome, which has to be a binary. So logistic regression can be used for binary prediction, and the most common application of logistic regression is to actually test a fit. So whether you can fit a binary outcome sample into using a logistic regression, and if it fits well, then it means that your data is well prepared. For example, like if it has a very low, low likelihood, or actually it's a very high likelihood, because you usually train logistic regression using a maximum likelihood estimate method. So if you have a very high likelihood, or if you have a very low negative log likelihood, which is the same thing as high likelihood, then it means that your data is your features well represent, or is well prepared to represent the binary outcome. And then you can actually study each feature, what they mean, and how well they are, how well they're fit, or how well they're estimated. And you can actually also do the confidence test, or like confidence interval test, or like various statistical analysis. But that's usually in the context of statistics, or not the machine learning perspective. In machine learning, what we're interested in is usually just getting an accurate prediction. So we're gonna take a look at the logistic regression in the context of machine learning, so making a prediction. And so it's okay. So it's a well-studied model. It's used since the 19th century. Analysis of coefficient of predictor variable is possible. So it is a rather straightforward model. And so I'm not going to go through the details. Hopefully you've taken at least the basic machine learning course, or you've taken my previous lecture, which was the programming for AI, opened last fall. So hopefully I don't have to go through the actual the formulation and all that. Question? Doesn't multiple occurred item have date-time information? Yes, yeah, that is true. So in order to answer that, we need to go back. So here, actually, yes. So let's say that this 7712 is code for body temperature, and this is a body temperature Fahrenheit, 화씨 온도. Then they actually do have timestamps. So this was measured like, I don't know, 11 a.m. This was measured 12 a.m. I know 12 p.m. This was measured 1 p.m. So you can actually sort them, and then if you want to, you can actually use all of them. You know, you can push them into the RNN or whatever to aggregate them, but that's all up to you. Or you can actually treat them as all like individual features. Like this was feature 42 at 9 a.m., 891 at 8 a.m., 891 again at 9 a.m., 1814 at 10 a.m., then 11 a.m., 11:30, 12 a.m., 12 p.m., something like that. So every single thing could be, you can just sort the entire items or the features in a temporal manner, hopefully, assuming that none of them occurred at the same time. And then you can actually push them all into the RNN to obtain whatever like patient status you want. So that's also possible, but usually in the ICU, patient vital signs such as like respiratory rates or heart rates or 산소 포화도, those kind of information is monitored or captured or measured very frequently, like every 5 minutes or something. So if you want to, if you have like 24 hours worth of data, or I don't know, if the patient stayed within the ICU for 3 days or 4 days, then you have the sequence would be gigantic. So the length of the sequence would be like in the thousands. So I'm not sure if you can, how you would treat them as an individual feature and then push all those 1,000 elements into the RNN. So you sooner or later you have to actually merge, like aggregate them at some point. So in that case, then you actually need to think about averaging, or minimizing or maximizing, that kind of stuff. This would be a part of your first project. So maybe you can think about this issue and while you're doing the first project. 혹시 답이 되셨나요? 네, 감사합니다. 네, 굉장히 좋은 질문이었습니다. 사실 다 인디비주얼 타임스탬프가 있긴 있어요. 그래서 그걸 어떻게 사용하는지도 또 다른 테크닉 중 하나입니다. 하지만 뭐 말씀드렸듯이 정답은 없어요. 그리고 어떤 태스크냐에 따라서 꼭 뭐 타임스탬프를 반드시 이용하지 않아도 되는 것들도 있고, 뭐 아니면 마지막에 발생한 정보만 사용해도 되고, 뭐 그렇습니다. All right, so moving on. All right, so yeah, the multivariate logistic regression that looks like has a model that looks like this, and usually, yeah, the base is actually just exponential, the natural number. So I'm just going so that's that. One thing I forgot to say. So logistic regression is, I said that logistic regression is used for binary classification, but it can be actually generalized into multi-class classification settings. And then multi-class logistic regression becomes a maximum entropy classifier if you are familiar with Maxent principles. But that's something that's out of scope for now. So I'm going to pile on. So yeah, this is just why logistic regression is, how logistic regression is derived, starting from the probability. So there's like if it's a binary classification, so there's the probability lies between 0 and 1, and then you can convert the probability to odds. So the odds is like how many, like out of sometimes what's like it is basically a ratio. So because this is the odds is calculated with the as a ratio where the numerator is the probability and the denominator is 1 minus p. So if your win probability is 0.8, like you're like betting or whatever, you're like doing a horse race or coin flip or whatever, and if your win probability is 80%, then the odds is 4. So you're 4 times as likely as winning to losing. And if it's 0.5, then the odds is 1. If it's 0.1, the odds is 0.111. So this is, so the range is what's important. Probability lies between 0 and 1, but the odds lies between 0 and infinity. So you can see the plots here. So this is, the probability has the domain of the probability 0 to 1, but the odds is like it can rise up to infinity, but the lowest is obviously 0. So that's that. And this is still not enough. So handling probability with like model is not very convenient because of the restricted range. You can relax that by turning that into odds, but still it is 0 to infinity. So the 0 is the lower bound, and this also becomes a nuisance. So you can actually convert this again by putting a log in front of it. So this is log of odds. So you put log in front of this, so that becomes a log of odds, or log of odds, which is equal to logit. So this logit, this is what's called logit. So if the win probability was 0.8, then your logit becomes this. And logit is, fortunately, has a range between negative infinity and the positive infinity. So now this is easier to handle with, parameterized models like logistic regression or support vector machine, where the weights can have any values, basically. So yeah, so the range of the outcome of the model can now become from between negative infinity to positive infinity. So before, if you had a parameterized model or whichever model, like prediction model, then that model's outcome had to lie between 0 and 1, which is quite a technical challenge. This also as well. I mean, you can think of ReLU kind of thing, but before ReLU, this was not very friendly. So you turn this into Logit, and now the outcome of the model can be any value between negative infinity and positive infinity. So this is your target value, basically. And then you simply say that your Logit value can be parameterized linearly. So it's a linear combination. So you have a bunch of features, and each feature has a coefficient or corresponding weight that you want to train, and so this is your assumption. Your Logit value can be linearly approximated, and then you put the log here. You put the log to this part, and then you do some basic algebra. So that the final outcome P is on the left side, and all the other is on the right side. So this is your final logistic regression formula. So then this is how. So why logistic regression looks like this? It's because you started from the probability, then you convert it to odds, and then you convert the odds to logit, and then you approximated the logit with you linearly approximated logits with a bunch of features, linear features. So that's why you have logistic regression formula like this. Hopefully, yeah, this is pretty straightforward. And obviously, you can convert this, or you can simplify this into an inner product. So if you look at this, then you can see that it's just basically you have a vector of betas or vector of weights, and you have a vector of features. The features being the x's. So you can write this part into an inner product, theta transpose x. So theta being the beta is actually, so it's just a different notations. So theta transpose x, and the rest is exactly the same. So this is where you plug in the vector that you prepared so far. So you did all those, basically manual labor. You went through, so you defined the task that you're going to do: hospital readmission prediction or ICU readmission prediction, mortality prediction, whatever. You defined the task, and then you went through the tables to extract relevant information, and then you constructed the triple nested dictionary to gather, to merge the information, and to actually create a label for individual samples, which becomes the positive label, which has a negative label. Then you vectorized your triple nested the dictionary. You vectorize the individual dictionary into a really long vector, and now you are using this vector to plug that into this here. So basically, that's it. So yeah, we're going to keep using this 40,000 dimensional vector, which was a representation of a single admission. So suppose that we are still doing a hospital readmission prediction task. So given this single admission, trying to predict whether the same patient will be admitted or will visit the hospital again within 30 days after discharge. So just as a reminder. All right. So yeah, so we have the X's ready, obviously. So we've went through like a lot of samples, probably like thousands or tens of thousands of samples, tens of thousands of patients, or actually tens of thousands of admissions. And then we've created a bunch of samples that look like this. So all we need is to estimate theta that best approximates the outcome. So because we have a data set that this has a corresponding, this vector has a corresponding label, because we also define the label, which is the readmission field in the dictionary. So this is X, and there's a corresponding Y. So what we want to do is learn or estimate the theta values that best estimates the relationship between all the X samples and all the Y samples in that sense. Yeah, so yeah, I need to learn this to correctly predict for X, or to correctly explain for X, which is just semantically the same thing. There's a question. Isn't it possible to include continuous value in the vector? Yes, obviously, yes, that's a good question. So these values are all categorical, or actually they were. So semantically, admission types and marital status and ethnicity, we said that we defined them to be categorical values. So only one of three out of three admission options, admit type options, only one can have one can have the positive value, and all the others are zero. Same deal with marital status, same deal with ethnicity. For diagnosis codes, multiple things could have a value of 1, and all the others are 0. So basically, all information here are discrete. But as I said as I showed you in the ICU admission representation, we can have a continuous value, which is length of stay. So if you were to vectorize this single ICU admission into a really long vector, then there would be a single dimension dedicated for representing length of stay, and you would simply just copy this value into that dimension. Or you can actually discretize them as well if you want to. If you want to, then if the minimum length of stay was like probably 0 day or 0. Let's say that the minimum length of stay was 0 and the maximum length of stay was I don't know, like 100. Then you can actually bucketize them or quantize them into just integers. So LOS 0, LOS 1, LOS 2, LOS 3. So there will be like 100 different options. And then that becomes a discrete value again. So you could do that if you want to, or you can simply just copy them 2.42 into this dimension. Or you could actually, if you want, you can normalize them as well. There's a lot of different things you can do with a continuous value as well. But the most straightforward or naive way to handle them is to simply copy this value into a dimension and then let the machine take care of it. So hopefully that's clear. 답이 되셨나요? 네, 감사합니다. So we were here, right? So yeah, this is a basic learning principle. So hopefully everybody's familiar with MLE, maximum likelihood estimate. Just gonna go through this pretty quickly as just a recap. So as I said, the objective is we have the X's, we have the Y's. So actually we have the Y's as well. So we have the X's, we have the Y's. So all we need to do is just train for the thetas, or estimating the theta values, which is a bit more statistical explanation. So need to estimate theta, and we want to learn or estimate the thetas based on the training pairs. So there's a bunch of X and Y pairs. So let's assume that there are n capital, like uppercase N number of training pairs. Then what we do is we want to maximize by when there's like infinite choice of thetas, because like each X vector is 40,000 dimensional. So theta are also 40,000 dimensional. And obviously there's like, in the 40,000 dimensional space, there's an infinite number of coordinates that you can use as a theta. So out of all those theta, we want to choose one theta one 40,000 dimensional a coordinate, which maximizes the likelihood of seeing X and obtaining Y for all samples. So that's maximum likelihood principle. So using that principle, we want to estimate the theta. So how we would do it is, so the loss function or the objective function is obviously likelihood function, because what we are trying to maximize the likelihood function. So this is your likelihood function, and we have n number of samples. So we're just gonna multiply. Then we're gonna assume that all the samples are independent. This is also an important thing. So all the samples are IID, so they're independent, identically sampled. So we can simply trying to obtain the joint likelihood of all the samples, we can actually treat them as independent samples and multiply all the individual likelihoods. So we can just simply multiply them, and then here the likelihood is following a Bernoulli distribution, because this is a binary prediction task. So we're gonna model the likelihood function with Bernoulli distribution, and of course there's still this product operator in front, and we are actually, so this is hard to multiplying this, like, n capital number n number of samples, which are probably very low values, like 0 point something values, and multiplying like them n times, then you would probably like fast approach a underflow error. So that's why we put the log function in front, or actually it's also for mathematical convenience as well. So put the log function in front, then this operator becomes a sigma, the sum operator. And this, if you think about it, I'm not gonna go through this, but if you think about it, if you put log function in front of this part, then that becomes a cross entropy function. Hopefully that's clear. Y can come from in front of the log, and 1 minus y can come in front of the log. I mean, you can first if you put the log, then this becomes like a log of this plus log of this, and then the exponent can come in front. Exponent can come from in front. Then that becomes y log your prediction plus 1 minus y log your prediction, which is basically a cross entropy. Yeah. So that's all. This is how everything is like all connected in the binary classification. So that's it. So that's all there is to it. So, and yeah, and of course, you have n number of samples. You want to normalize them by putting a n to the negative 1, which is just 1 over n. So 1 over n, you normalize them, and then so simply you take. So this is your log likelihood function, and you want to maximize them. So how you would maximize? You want to maximize by changing the theta value. So how you would do it is you just use a gradient-based solution. You just you can use a gradient ascent method to estimate theta value, or conversely, you can put a negative the minus sign in front, then this becomes a negative log likelihood, NLL, which is what you've seen so many times in the machine learning model. So you put you put the minus sign here, that becomes a negative log likelihood, and then that you need to minimize, because minimizing the NLL is maximizing the log likelihood. So put the minus sign here, then you can use gradient descent algorithm. Any gradient descent algorithm you want to. You could just use SGD or Atom or Eta Delta, Eta Grid, whatever. Or if you want to go fancy, you could use like conjugate gradient descent or whatever. So that's basically how you would obtain the values of theta. All right. So any questions so far? This is like all very basic stuff, right? Hopefully, yeah. Yeah, if you have any question, you can simply type them on the chat box as well. So don't be shy. If you have any question, you can ask them. But I'm just going through them in a bit of a hurry, because I'm assuming that a lot of people already know this, and I don't want to spend too much time on the mathematical details, because yeah, this is a bit more like a high level class. So yeah, one thing about the logistic regression is after you've trained your coefficients or your weight, the thetas, in this case, the betas, then you can actually simply estimate or you can infer or you can study the relationship between individual features and the final outcome. So for example, if a certain beta I, so which is the coefficient for the ith feature, if beta I is positive, then you can readily say that, oh, xi, the corresponding feature, that feature itself, not the value, but the feature dimension itself is positively correlated to the outcome or the success in this case, because we were doing with the coin flip thing. So if beta I is positive, then the corresponding ith feature is positively correlated to the success. So in the biomedical or the healthcare context, we can say, for example, if xi was obesity, so if the patient is obese or not, so it's a binary feature. So if the patient is obese, it's a 1. If the patient is not obese, it's 0. Obese being 비만입니다. obesity는. 이제 비만 환자면 1, 비만 환자가 아니면 0이라는 피처를 갖게 되겠죠. 근데 이제 걔의 베타, corresponding, if obesity's corresponding weight was positive, then it means that the obesity is correlated with the outcome. So let's assume that the outcome is heart failure prediction. So we're trying to predict a heart failure with logistic regression, and the obesity's corresponding beta was positive, which means that a patient who is obese has more likelihood of being classified into the heart failure case, heart failure label. If the corresponding feature is negative, then it means that it is negative correlated to the success, to the outcome. So in the heart failure prediction case, if the high income, so again, let's say that this is a binary feature. So xi is whether the patient has high income or not. So if the patient has a high income, 소득이 높으면 1, 소득이 낮으면 0이다 그러면 이제 그런 거죠. So if the corresponding weights or the coefficient is negative, it means that the high income is negatively correlated with heart failure. So it simply means that if you have high income, then you're less likely to be classified into the heart failure label. So that's simply it. So one thing that we need to take care is that coefficients do not represent causality. It's just simple correlation. So just because beta I, let's say that the xi is obesity feature, and just because beta I is positive doesn't mean that obesity leads to heart failure. It just means that whoever had heart failure and whoever, like patients who had heart failure, there was a lot of positive samples that also had obesity as 1, and conversely, it means that the samples who did not have heart failure, the label Y becoming 0. If patient who did not have heart failure, a lot of samples in that class did not have obesity set to 1. So that's simply it. It doesn't mean that scientifically obesity leads to heart failure. Same thing. If this is negative, like for example, in this example, it doesn't mean that high income prevents heart failure. I mean, it might. I mean, again, so this is just because it does not represent causality does not mean it is not causality. It might be the case that obesity does lead to heart failure. 비만인 사람은 정말로 심장병에 걸릴 수도 있잖아요. 이제 이 인과관계가 있을 수도 있는데 없을 수도 있는 거죠. 그러니까 그건 알 수도 없는 거예요. 이 로지스틱 리그레션만으로는 그건 알 수가 없는 거예요. 그냥 단지 이제 실제로 이 심부전 환자들의 포지티브 케이스니까 이제 실제 심부전 환자들 중에는 그냥 비만인 사람이 많았고, 실제 심부전 환자인 사람들 중에는 고소득자가 별로 없었고, 단지 그거일 뿐입니다. 실제로 소득이 많으면은 뭐 심부전이 덜 걸릴 수도 있겠죠. 뭐 예를 들어서 병원에 자주 간다던가, 뭐 헬스를 돈 내고 한다던가, 뭐 그런 걸 할 수 있으니까 돈이 많으면 뭐 헬스에 덜 걸릴 수도 있겠죠. 근데 뭐 이것만으로는 그걸 알 수가 없다는 게 핵심입니다. 이제 그걸 헷갈리시면 안 돼요. So it's a very important concept. So please, this goes same with any training, classical prediction models or neural network models as well. Like if you use support vector machines or random forests or even decision trees, decision trees are highly explainable. Doesn't mean that the features are causal. It doesn't mean that it's a causal model. Same with RNNs, convnets, transformers, whichever. It doesn't mean none of the models are causal models. So, but again, that doesn't mean that the features are not causal. It just means that studying the trained model doesn't give you information about the causality. That's it. Yeah. So again, and precisely calculating the significance of a feature. So whether this is positively correlated or negative correlated, you can simply look at the coefficients and then simply tell that, oh, so like, you know, x1 feature x1 is positively correlated to the outcome and x2 is negatively correlated to the outcome. But how important each feature is a bit more complicated. So you can still do this, but it needs a bit of a computation. But so it doesn't mean that, so just because beta is large and beta is small doesn't mean like individual betas having a large value, small value, doesn't mean that it is like significant, because it's you should take a look at, you should think about it in a relative context, because a lot of betas could be, you know, have a high absolute values, or a lot of betas could have, you know, very small absolute values. So you need to take that into account. But simply just binary classification of positive correlation and negative correlation, you can just read the beta values and that's it. All right. So I'm going to move on. Right. So the evaluation, once you've trained the model, then you need to evaluate or measure how well your trained model is. So this does not anymore pertain only to the logistic regression. Any binary. So this is I'm gonna, you know, use the binary prediction example. I'm just gonna run with this example, and this evaluation is relevant. It is associated with any binary prediction model. So like support vector machine or whatever. But whichever binary prediction model you've trained, you need to evaluate it. And if you, for example, if you were to deploy your trained model, let's say that your model is like, you know, 99% accurate or whatever, and you want to sell that to a client, you could either sell it to a hospital, or you could sell it to like a whatever IT company or whatever. And you need to decide which threshold you would use for binary prediction. For example, so you need to, for example, you need to raise an alarm. Let's say that you have a mortality prediction model. So you train the model that can predict whether the patient will die within the ICU stay or not. So, and the model would obviously produce a value between 0 and 1, because it's a binary prediction model. And at which value should you raise the alarm so that the physicians can attend to the patient? Should all samples that produce value higher than 0.3 should they all be considered true, like, you know, positive samples? And so should all models, like if any sample produces a prediction score of 0.3 or higher, should we raise the alarm, or should the threshold be 0.5? Should the threshold be 0.7? It's really hard to tell. So that's where we need to use we're going to carefully evaluate the prediction performance of the model. So in this case, we can use something called a confusion matrix, and this is still a readmission prediction task. So we can actually have 4 cells. So this is this axis. So the rows represent predicted class, readmitted and not readmitted, and the columns represent actual class, so readmitted, not readmitted. So this is the prediction. This is the ground truth. And obviously, if you predicted positive and that patient did really end up being readmitted to the hospital, then that is a true positive. So that's like a very good scenario. And also, if you go diagonally, if you predicted, no, this patient is not going to end back up in the hospital, and that patient did not visit the hospital again, then that's true negative. So this is true positive, true negative. So these are the ones that you want to maximize, and these are the falses. So if you thought that but if your model thought that this patient is going to be readmitted, but actually the patient did not get readmitted, then that's a false positive. So it's false alarm. So you are too worried, and this is the inverse case. So the model predicted, no, this patient is not gonna be readmitted, but in reality, the patient did end back up in the hospital. So this is a false negative. And in a lot of cases in healthcare, this is way more false negatives are way more critical or something that you really want to avoid compared to false positives. For example, let's say that you have a cancer prediction model. So your model predicts whether the patient is going to be diagnosed with cancer or not, or whether the patient will develop a certain cancer, like lung cancer or whichever cancer. So it's a binary classifier. And if you think about it, do you want your model to have a high, let's say that's a zero-sum game. You either have to choose a high false positive or high false negatives for your cancer prediction model. Then which one would you choose? Would you rather have your model have high false positives and low false negatives, or would you rather have your model have high false negatives and low false positives? What would be your preference? Okay, so if there are, this question is, I guess no, and there are no answers because this is such an easy question. So obviously you want your false negatives to be lower. I mean, if you had to choose, the ideal model would be, you know, 0 false negatives and 0 false positives and just 100% trues all the time. But in reality, that's not the case. So you have to either choose one, like either you had to choose one over the other. So if your cancer prediction model has a high false negatives but so low false positives, that means that it is just predicting, like, you know, predicting no most of the time. Like now this, like for all the patients, if it simply says no, this patient is not going to have cancer, no, this patient is not going to have cancer, then obviously it would have a very low false positives because there's no false alarm at all. It will just have a lot of false negatives. Even for the patients that needs to be treated or that needs to be taken a look at, it's going to be ignored, and then sooner or later that patient is going to actually end up in a hospital in a very severe state. Compared to that, if you have a high false positives but low false negative, it means that the model is just constantly predicting, frequently predicting, yes, this patient is going to develop develop cancer like most of the time. Then you're not going to miss any patient, but that you're just constantly going to raise the alarm. So it'll lead to a lot of alarm fatigue. So like the doctor is going to always be alerted, this patient is going to develop cancer, so you need to take a look at the patient. So eventually the doctor is going to have to look at all the patients for the possibility of developing cancer, which would lead to, you know, just exhaustion of the caretakers, exhaustion of the nurses, exhaustion of the physicians. So that is also not a good thing. But compared to actually losing patient life, maybe that is a bit more acceptable. But both, yeah, but the ideal case would be just low false negatives and low false positives all the time. There was a question: low false negative at the first prediction, low false positive at the last prediction. Low false negative at the first prediction, low false. What do you mean by first prediction and the last prediction? How would you know when is your first prediction and when is your last prediction? So I mean, first prediction is, yeah, like you have a patient coming to the hospital, and then you plug the patient information into the model, then that becomes the first prediction. But how would you know when is the last prediction? 스크리닝 앤 정밀 검사. 그러니까 이제 첫 번째는 이제 단순 테스트, 그러니까 이제 그냥 단순 테스트는, 스크리닝은 최대한 많은 거를 검출하고, 그다음에 이제 정밀 검사, 정말 시간 많이 들고 돈 많이 드는 거는 이제 low false positive. 네, 그러니까 이제 그 false alarm이 없어야 된다라는 얘기인 거죠. 네네. 맞는 것 같습니다. 그렇게 굉장히 리즈너블한 얘기인 것 같습니다. 그러니까 똑같은, 근데 요 경우는 그럼 이제 클래시파이어가 두 개가 다른 거죠. 이제 보통은 제가 얘기한 건 이제 하나의 클래시파이어가 있는 경우인데, 예를 들어서 지금처럼 처음에 딱 병원에 와가지고 뭐 단순하게 그냥 이 사람의 뭐 흡연 이력, 뭐 여러 가지 어떤 뭐 가족 병력, 뭐 단순한 뭐 몇 가지 체크를 해봤을 때 이제 프리딕션 하는 모델이 따로 있고, 그 다음에 이제 뭔가 문제가 있을 것 같다 그래가지고 뭐 MRI도 찍고 뭐 CT, 뭐 펫스캔도 찍고, 그 다음에 뭐 막 혈액 검사도 하고 뭐 그래 가지고 나오는 굉장히 그 리치한 데이터를 가지고 또 클래시파이는 모델이 따로 있는 거잖아요. 그래서 그 두 모델의 이제 objective가 사용 용도가 달라야 된다라는 얘기인 걸로 네. 얘기를 하면은 네, 아주 뭐 저는 동의할 수 있을 것 같습니다. 네. It's a good point. All right, so this was the confusion matrix. So moving on, so this just the definition. So I just wanted to explain the definition of TPFP, FN, and TN. So using this, there's a lot of variety how you can combine them so that you would have a single scalar value that represents the prediction performance of your model. So accuracy is obviously the most popular metric. So accuracy is just simply you add all denominator in the denominator. You add all cells. So this is simply a count, like how many true positive, how many false positive, how many FN, how many TN. So this is simply a count. And if you add all things up, all the values in all four cells, then that becomes your entire number of samples. So out of all the entire number of samples, how many true positive and true negatives did you get? That's the accuracy. But accuracy is obviously not appropriate for imbalanced classes. So for example, again, let's go to readmission prediction. So if only 10% of your samples has positive cases, so only 10% of your training set or your data, or 10% of your patients ended back up in the hospital or revisited the hospital, then that is severely imbalanced classes. So in that case, accuracy is obviously, if your model simply just predicts 0 or no readmission all the time, then it's gonna achieve a 90% accuracy because the positive cases are so rare. So obviously, accuracy is not appropriate for imbalanced classes. So there are some other measures that we could use in that cases. So before we go to that, there are also other combinations of TPFB, FN, TN. So precision is you add TPFB, so you add these. So this is the samples that the model predicted as positive. So out of all the positive predictions, how many were the actual positives? So this is precision. Sensitivity, or which is called recall, or true positive. I mean, sensitivity is what's usually, so recall is used in the data mining or search engine community, or recommendation. So basically, like a bit more computer heavy domain. Sensitivity is used in the biomedical domain all the time, but they're the same thing. Sensitivity and recall. That is out of all the samples, so TPNF, and out of all the really positive cases, true really positive cases, how many did you actually get? So it's just, out of all the actuals, out of all the actual positives, how many did you actually predict that positive? So it's just, that's why you call recall. And there's also specificity. So this is true negative rate. So this is the denominator is TN plus FP. So TN plus FP. So TN plus FP is, so out of all, so this is all the samples that are actually negative. So this is all negative samples. And out of that, how many did you actually predict true negative? So this is like the inverse of recall. So if you read like the literatures or papers, and especially in the biomedical domain, you would see sensitivity and specificity all the time. And especially they are used, sensitivity and specificity is combined to give you a score called AUROC, which is area under the receiver operating characteristics curve. So in this case, one axis is true positive rate, which is again recall. True positive rate is recall. So one axis is this. Another axis is false positive rate. Sorry, false. So which is 1 minus specificity. So the 1 minus true negative rate is false positive rate. So 1 minus specificity. So this is one axis. This is one axis, and you are trying to, and you measure the, so when you have a prediction model, you can set different thresholds. Like the threshold could be 0.1, 0.2, 0.3, or it could be 0.11, 0.12. There is infinite number of thresholds you can use, and you adjust or you change the threshold values and measure the sensitivity and 1 minus specificity, and you plot that on your two-dimensional plane. So when the threshold is like 0.2, then the true positive rate is like 85%. 85%, yeah. So it's about 85%. And oh, actually, I'm sorry. So I'm sorry. So the threshold is not actually seen here. So the threshold is hidden, but when you adjust the threshold at certain point, the true positive rate would be 80%, while the false positive rate would be like 17, 18%, something like that. So you move the threshold around and you can plot this value. And the larger the area under this curve, under this orange curve, the better the performance of the model. So if the plot was a simple diagonal line, that means that the area under this diagonal line would be 0.5. So we're assuming that this is like the range between the range of the y-axis is 0.0 to 1. The range of the x-axis is also 0 to 1. So the complete area, the total area is 1. It's just simply 1 times 1. So it's 1. And if you half them, then it becomes 0.5. So if you obtain a 0.5 or 50% AURC, that means it's random guessing. So there's the model is just completely randomly guessing 0 or 1, and it's just regardless of which sample is coming into the model. So you want this curve to be as higher as possible, which means that you want to maximize the AURC value. So that means that while detecting true samples, while frequently or while your model is well detecting the true samples, it is also minimizing the false positive rate. So it is not making false alarms too frequently, which is a very ideal situation. So that is AURC. There's something called AUPRC as well. So AUPRC is a bit different. So AUPRC, area under the precision recall curve. So in this case, one axis represents precision, another axis represents recall. So recall is the same as true positive rate. So this recall is again used as one axis, but the another axis is not a false positive rate, it's a precision. So again, you can change the threshold and then plot the curve in this one by one area, one by one two-dimensional plane. And obviously, just a couple examples. So if your recall is 0, it means that your precision would be 1. If you think about it. So if you always, it's easy to achieve very high precision if you're willing to sacrifice your recall, and vice versa. If you're willing to sacrifice your precision, you can actually detect a lot of true samples. So it is so again, so the curve looks a bit different from this guy, and 0.5 AUPRC is not random guessing at all. Random guessing would be actually here, like in this low line. So random guessing. So if your precision is 0.5, then it's as good as random guessing. Like if whichever threshold you use, if your precision is always 0.5, it means that it is randomly guessing. So 0.5 AUPRC is actually a very good score. It's way better than random guessing. And if you have a AURC and AUPRC, which are a better metric for measuring evaluating the performance of a binary classification model when the classes are imbalanced. So which one is better metric, AURC or AUPRC? Which one should you use? The answer is actually, I think this is a typo. I'm sorry. Well, so I guess this is a bit an ambiguous statement, but according to a paper here, which was published in 2015, AURC, even if your data is like heavily class imbalanced, you can still get a decent AURC. But AUPRC is not. It's really hard to get good AUPRC under severely imbalanced classes. So so back to the basic, if your data is 50-50, there's like 50% positive cases and 50% negative cases, you can simply use accuracy to measure the performance of your model. But if it's a bit class imbalanced, then you could use both AURC and AUPRC. But if your data is severely class imbalanced, like if there's only 1% of true cases, 1% of positive samples, or if there's like 0.5% positive samples, in that case, you can easily increase the AURC because the positive cases are so rare, you can hardly get let's see. So yeah, you can easily get the true positive rate really high while somehow minimizing the false positive rate. So in that case, you can easily get like 80% or 90% AURC. But AUPRC on the other end is really hard to get better, really hard to get like a 0.5 or 0.4 AUPRC when the class is severely imbalanced. And if you think about it, you need to actually detect or retrieve the positive samples while maintaining very high precision rate, very high precision scores, which is really hard. So if you think about like search engine, so AUPRC is a bit more because recall and precision recall is a bit more widely used in the search engine community. So if you think about it, your query to the for example, let's say you're using Google search engine and you put very specific queries like let's see. I don't know, the cost of a GPU RTX 3090, something like that. So that would be a very specific query. You want to look for how expensive RTX 3090 graphics card costs these days. So that is very specific query. And Google contains probably trillions or gazillions of HTML documents in their server. So out of all those infinite number of web pages, only a very small fraction, like 0.0000001% of the entire web pages that they possess are going to be relevant to your query. So that in that situation, Google search engine has to rank the infinite amount of zillions amounts of web pages by the order of relevance to the query, which is the cost of RTX 3090. So in that case, in that situation, it's really hard. It's really important that you maintain both recall and precision at a really high score. So that's why AUPRC is a bit more a strict measure when the class is really, really imbalanced. So F1 score is something that you can use again by combining precision and recall. So, but you still need to have a threshold. So it's just a harmonic mean between precision and recall. So F1 score is just like a combination of precision and recall. So, but you need to again set a threshold. So actually, there's something called maximum F1 score, which is just varying the threshold, and you just take the one that has the maximum, that produces maximum F1 score. So something to keep in mind. You would see F1 scores sometimes in the NLP domain as well, because NLP is usually very high, very closely tied together with the text processing or search engines or retrievals or recommendation. So in a lot of cases, you would see F1 score as like a secondary measure of the secondary measure of the prediction model or classification model. All right, so this is it. So hopefully we have all the weapons that we need to actually measure or evaluate the performance of the binary classification model. And you can obviously you can easily expand or generalize AURC and AUPRC into a multi-class setting. You can look up the scikit-learn webpage to how you would do it, and I'm not going to go into the details of that. So we have a bit more time. Actually, I should have uploaded the next slide to the classroom. So let's see. So this is hopefully using today's class and one more class next week. We can tie all the things up in all the things up that we need to learn about the predictive model and actually do the project. So let me actually upload this to Classroom right now, so that people who want to download the slide, the material, and want to annotate or whatever, if they want to use it. Give me just a second. Let me just upload quickly this to Classroom. All right, I just uploaded the slides, so I'm gonna give you guys a couple of minutes to download it. Please let me know if you guys are ready. 혹시 아무나 다운받으신 분, 다운받으셨으면 알려주실래요? 네, 알겠습니다. All right, let's move to week 4 material in advance. So far, we've covered all these preliminary. So these are preliminary stuff, because the actual fun begins when you've covered all this and you can, freely define your own prediction tasks, and then you can extract pre-processed data on your own to create a cohort or like a data set. Then you can vectorize them, and then you can once you can do that, you can use any model you want. You can actually do a lot of really interesting research. You can actually come up with a lot of interesting research topics as to how you would come up with a better model, or how you would minimize the pre-processing steps, or how you would automatically pick the best features. Like a lot of different stuff. But in order to do that, you actually need to be able to freely do all these previous tasks. Right. So yeah, so far we've looked at the logistic regression and the evaluation of the binary prediction model. So now we can dive into deep learning models. And this is, hopefully this is like all like very, very easy stuff. I'm just going through this in a very like small, like step by step, just because I don't want anybody to get confused or have a hard time when doing the first project. So, but the descriptions of the deep learning and all that would hopefully a lot of people are already very familiar, because if you had taken my class programming for AI, this is very like piece of cake for you guys. So modeling. So classical approach, we took a look at the logistic regression. In deep learning approach, we're going to look at the neural networks and what the hidden representation means in the in the biomedical, in EHR. And then we're going to move on to recurrent neural networks, because in the first project, we're going to use RNN. So that's it. Yeah, I'm going to skip through this. So this is a single. So this is single neuron. So single neuron. Hopefully, nobody's really. So single neuron, yeah. So single neuron, there's a like bunch of. This is a single neuron. This is not even a multi-layer perceptron. It's just not even multiple perceptron. It's just single neuron, and in the neuron, you can obviously there's a lot of things coming in and then firing the output. So again, a lot of things coming in, which are actually different features. So there's feature x1 to x2, xm. So there are m number of features, and each feature has a weight tied to it, a weight associated with it, and then multiplied by that, then this single neuron aggregates information from different features, and then there's a bit of bias into it, which is simply just, you can think of this as, x0 bias being the x0 being 1 all the time. So there's a bias, and then there's a single activation. After you've done the aggregation of all the features weighted by the weights, you have a activation function, which should be nonlinear, in order to increase the expressivity of your neuron, which is typically a sigmoid function. Back in the days, like these days, people use ReLU, GalU, CellU, or switch function or whatever. But back in the day, it was only 10H or sigmoid. So activation function being sigmoid, then so that is a single neuron output. And obviously, if you think about the human brains, there's like trillions of neurons all like tied together. So if a neuron fires its output, then it becomes input to the next neuron, one of the inputs to the next neuron. So one of the inputs, like this could be seen as like output, M output from the previous M neurons. So it's like all like tied together. So that's basically why we have a neural network that mimics the behavior of the human brains. So in our case, we have, again, the 40,000 dimensional vectors. So this is admission prediction, readmission prediction. And now this M becomes 40,000. So let's say that you are simply putting a 40,000 dimensional vector into a single neuron, and the single neuron has let's say that you're using sigmoid function as an activation function, then this is actually just a logistic regression. So logistic regression is actually just a single neuron with a sigmoid function used as the activation function. So that's it. So it's just a simple analogy between single neuron and the logistic regression. So if you have a multiple layers of neurons, then there's like, so there's 1, 2, 3, like k number, k number of neurons in the hidden layer. So now it's more than just a logistic regression, because before a single neuron was, I'm sorry. Yeah, sorry about this. So before, in the previous slide, we've established that a single neuron is equivalent to logistic regression when the activation function is sigmoid. So there's how many? There's 1, 2, 3, like k number of sigmoid, k number of logistic regressions that also is tied to the final output. So that's what basically a multi-layer perceptron looks like. And if you look at this, let's just use 4 neurons in the hidden layer. So this is your input. So there's still the 40,000 dimensional input is your input, and then your the middle layer, the hidden layer, has 4 neurons, and the final layer or final output should be obviously just a scalar value between 0 and 1, because this is a binary classification. So you can think, so the first feature, xi or x1 is tied to, x1 is pushed forward to the 4 neurons like this. So it has a weight tied to the first neuron, first weight here, the first x1 has a weight tied to the first neuron here, another weight tied to second neuron, another weight tied to the third neuron and fourth neuron. So there are 4 weights here attached to x1. Same deal with x2. So x3 all the way towards the final feature. So out of all the individual features in 40,000 dimensional space, they are all tied to 4 weights, each weight corresponding to a single neuron in the hidden layer. So this becomes, there's a 4 by 40,000 parameters between input and hidden layers. So this is all like very obvious stuff. So it means that there is 4 by 40,000 dimensional weight matrix, right? Hopefully this is clear. So 0 has 0 multiplied by this guy goes to this guy. 0 multiplied by this guy goes to this guy, right? So this is all very simple stuff. If you think about the, how the vector multiplied by matrix is done, the matrix vector multiplication is done, then if you think about it, this is a binary. So this is a binary vector, binary 40,000 dimensional vector, where most of them are zeros and very few of them are ones. So if you think about how vector and how matrix and vector are multiplied, you can see that none of the weights, 4 weights in the first column will be used, because the first column, the feature that corresponds to the first column is 0. But the feature that corresponds to the second column, which is x2, is 1. So this column, or this row, actually, this row is used. This one, all the 0, 0, 0, 0, 0, 0, 0, like these 4 features are all 0. So the corresponding 4 rows are not used again, and this corresponding feature is used. So if you do the multiplication, if you do the matrix vector multiplication, what it amounts up to is actually just summing a rows of the weight matrix, where the row is selected by which feature is active and which feature is not. So that's it. So this is a bit simple case, because the feature vector is binary, so there's only 0 and 1. So you only select the rows that has a active feature, and that's it. Then you take this, you take this, you take this, and then you simply sum them up, and that becomes your next hidden representation vector, like this. So you sum them up, and then that becomes your individual neuron value. So 4-dimensional, each going to each neuron. So that's it. And obviously, if you have a continuous value somewhere, like 1.5 or 1.6, whatever, that also will activate the corresponding row. So if this was to be like 2 instead of 1, or 2.5 instead of 1, then this row is still active. It just means that this row is weighted by that amount. If this was 2.5, it's just 2.5 times this amount, this vector, this row, and that's it. So again, the same principle. If the feature is 0, it means that that row is not used. So the same principle persists. All right. So after this, you have the nonlinear activation function, which is whatever, ReLU or sigmoid function, whatever. It goes after it passes through the nonlinear activation function. Then that becomes your latent representation or hidden representation. So that is what hidden representation means. So it's simply sum of the rows that corresponds to active features that passes through a nonlinear activation function. That's what hidden representation is. So you can actually think about them as you can think about the red thing as a embedding of this feature, or representation of this feature. So when you have, when you do natural language processing, you have a word embeddings, right? So you have like a embedding for dogs, embedding for cat, embedding for boy, whatever. You have a vocabulary or dictionary, and individual word has a corresponding embedding vector. So this is the same deal here. There are 40,000 things that are possible. There's like a admission type elective, admission type emergency department, admission type other, marriage status single, marriage status divorced, marriage status widowed, whatever. Like there are 40,000 different things that can describe a single admission. So it means that you have 40,000. You have a dictionary of 40,000 words, or vocabulary with 40,000 words, and each word has a corresponding embedding. So this is an embedding that represents a emergency department admission type emergency department, and this embedding represents, which is this, I think it was married. So this embedding represents a marital status of married. That's it. So this is you can think of this as a lookup table in the TensorFlow or PyTorch. So you have the embeddings, you add them up, and then you push them through the nonlinear activation function, and that becomes your hidden layer, or that becomes a latent or four-dimensional compressed representation of your admission. Yeah, of your admission. That's it. So originally, your admission was represented as a 40,000 dimensional, very interpretable vector, but now you're compressing them into four-dimensional vector. And then once you have the four-dimensional vector, so once you have the compressed latent representation of your admission, then you can use a sigmoid function. So then you can do the same thing. There's like, you have the 1/4 weight vector here, and then you have the sigmoid function as the activation function, and that becomes your output. So you have the so that becomes this is another logistic regression where you no longer use a 40,000 dimensional vector as the input, but you use a four-dimensional compressed latent representation of your admission as the input to your logistic regression. I think that was a question. representation, so 춘경님이 물어보시기, representation이라는 용어는 모든 각 히든 레이어의 피처 벡터를 의미한다고 봐도 되나요? 모든 각. 그렇다고 볼 수 있습니다. 그렇죠. 그러니까 이제 여러 개의 히든 레이어, 저희가 지금 이제 히든 레이어가 하나밖에 없었는데, 예를 들어서 히든 레이어가 하나 더 있다. 근데 걔도 또 4디멘셔널로 보낸다. 그러니까 이제 4디멘션을 보낸 히든 레이어가 있으면은 다시 또 거기 사이에 매트릭스가 4x4 매트릭스가 있을 거 아니에요. 그때 이제 각 로우는 이제 이 첫 번째 4디멘션의 각 피처를 대표하는 임베딩이 된다고 레프레젠테이션이 된다고 볼 수도 있겠죠. 근데 더 이상 이제 그게 인터프리터블 하지가 않죠, 그다지. 왜냐하면 여기서는 이제 처음에 여기서 이제 얘가 여기에 해당되고, 요거는 이제 이머전시, 이제 응급실로 실려온 어드미션 타입이다. 요거는 어디냐? 요거는 이제 결혼한 상태를 나타낸다. 뭐 이제 그러니까 메리지 타입이 여러 개 있으니까 이제 결혼 상태 중에서 결혼함을 대변하는 레프레젠테이션 벡터다라고 알 수 있지만, 이거 이제 이거 이제 4디멘션을 보냈고 또 다시 이걸 예를 들어서 2디멘션을 보낸다. 다음번에는 2디멘션 보낸다 그러면 그때 얘가 이거랑 이거 사이에 4랑 2 사이에 4x2짜리 매트릭스가 있을 거 아니에요. 그때 각 로우가 요거가 뭘 의미하는지 사람이 알기가 어렵죠. 이전에는 각각이 뭘 의미하는지 명확히 알았는데, 이번엔 얘가 뭘 의미하는지 사실 정확하게 알기 어려워요. 근데 어쨌든 얘를 하나의 피처라고 본다면은 그때 4x2 매트릭스 각 로우는 말씀대로 요거의 레프레젠테이션이라고 볼 수도 있습니다. 네, 감사합니다. All right, so just to summarize what I just described to Chungyong Lee is that if you were to push this into another hidden layer, which is let's assume that that second hidden layer is two-dimensional, then there would be a 4x2 weight matrix, and in the same principle, each row in that 4x2 matrix would be like an embedding that represents this individual feature. It's just that it's difficult to understand what this feature actually means. In this case, we exactly knew what each individual feature meant. Like this was admission type emergency room. This was marriage status type married. So we exactly knew what they meant. But in this case, we don't know what this individual four-dimensional features mean. So it's hard to interpret. So that's why why people say neural networks are hard to interpret. All right, so hopefully that's it. Right. Oh yeah, this is just a comparison between how logistic regression is done and how MLP, multi-layer perceptron, or feed forward neural network is done. So just before we directly plugged in the 40,000 dimensional vector into a single neuron, but here we're compressing this into a lower dimensional space to obtain a latent admission representation, and then you're plugging that into the logistic regression. That's basically it. I think we have, yeah, we have maybe a couple more minutes though. We don't have a lot of, yeah, so we have, I think we can cover the remaining 3 or 4 slides. So training is done by, obviously this is done by backprop. So you have a outcome Y, you have a sigmoid function, and obviously there should be like some nonlinear activation functions, assuming that, let's assume that there's sigmoid functions as well. So there's sigmoid function here, and then all what you need to do is estimate the parameters of weight matrix here, which is 4 by 40,000 dimensional weight matrix. I'm sorry, so actually no. In this specific example, what we're saying is, I guess this is a typo actually. Yeah, this is a typo. I'm sorry. So there are how many thetas or how many weight parameters do we need to estimate using a maximum likelihood principle? There is a gigantic matrix here, which is 4 by 40,000, and there's one vector which is 4 by 1. So there's in total 4 times. So this is a typo. So this is 4 times 40,000 plus 4 parameters that we need to estimate using the maximum likelihood principle. And we're not going to do that on our own. We are going to just we're going to simply use backprop, the backprop function, the autograd function of the PyTorch and TensorFlow. So the principle still is the same. There's we model the likelihood function as a Bernoulli, and then we put the log in front of it. Then we have a cross entropy function. Everything exactly the same. All right. Yeah, we want to minimize this cross entropy. So putting the log in front of here, we get this. That's it. But we need to apply a chain rule, because Y is the output of this guy, and this guy this guy has inputs of 4, but these are the outputs of this layer. So we need to apply a chain rule and update using the backprop. So that's it. So in practice, computer does backpropagation for you. You don't have to do it on your own. So you have the autograd packages. So there are a lot of programming languages. I mean, deep learning libraries out there. There's Theano, which is no longer maintained, but which was probably one of the very first deep learning library developed in Yoshua Benjel's lab by the engineers. So there was Theano in the very early ages, and then TensorFlow developed by Google, PyTorch developed by Facebook. So before PyTorch, there was actually Torch, but Torch was written in this language called Lua. So I think Facebook converted that, actually wrote a Python version of Torch. So that is why it's called PyTorch. And there's also MXNet, which is, I think, maintained by Amazon. There's a lot of different, like there's Caffe, there's I forgot, there were a couple of others as well. But these days, I think a lot of people most people, especially students, are using PyTorch because it's just easier to handle. Yeah, I'm not gonna, just a high level concept of how they can do backpropagation for you automatically is that Theano, TensorFlow, PyTorch, they're all just neural network model represented as directed cyclic graph. So neural network is just it is basically a graph. There's like input and there's the output. So you can represent them as a directed cyclic graph where each node contains some mathematical operation, like some multiply or like some value, a value or whatever. There's like a single operation in each node, and then each node contains the derivative of the math operation. So then once you have that node, like once you have a graph of nodes that contain these information, you can do the backprop, using a chain rule. I've already, I'm not going to go into detail how PyTorch can do this kind of stuff. If you're interested, you can actually go refer to my previous programming for AI lectures, which is all uploaded on YouTube. So if you're interested, you can just ask me the YouTube playlist, and I can give it to you. All right, so this is the end of class today. Starting from next Tuesday, we're going to look at how we can use recurrent neural networks to be a bit more fancy. So we're going to use a sequential data. Last question. So 승우님, 류승우님, continuous value가 initial vector 끼어들었을 때 비슷비슷하게 weight를 initialize 하면은 레이어에서 더 큰 영향을 주는 것 같은데 주게 되는 것 같은데 이것은 justifiable한가요? 그러니까 그 말씀이 이제 뭐 다른 애들 바이너리 이미지 1010인데 뭐 하나가 막 뭐 바디 템퍼리처가 100 뭐 이러면 이제 그게 이제 그 스케일이 안 맞는다는 그런 말씀이신가요? 네, 그럴 때 이제 아까 말씀드린 대로 노멀라이즈를 해도 되고요. 이제 바디 템퍼리처를 다 모아다가 그 뭐죠, 빼기 뮤 나누기 스탠다드 디비에이션 해가지고 노멀라이즈 하셔도 되고요. 그게 아니면 아까 얘기한 대로 퀀타이즈를 해도 되고, 바디 템퍼리처가 뭐 이제 34도부터 35도까지 한 버켓, 35도부터 36도까지 한 버켓, 36도부터 37도까지 한 버켓, 뭐 이런 식으로 이제 버켓을 만들어서 아예 그냥 카테고리컬 베리어블로 만들어도 되고요. 그거는 이제 여러 가지 테크닉을 쓸 수가 있습니다. 근데 가장 흔히 쓰는 거는 네, 보통 노멀라이제이션을 하거나 아니면 퀀타이제이션을 하거나 그 둘을 제일 많이 씁니다. 혹시 답이 되셨나요? 네, 알겠습니다. All right, so yeah, it's if there are no more questions, this is the end of the class today, and I'll see you guys next Tuesday, and hopefully by next Tuesday we can finish this all up, and on next Thursday we can talk about the specs of the first project. So have a good weekend, you guys, and I'll see you guys next week. Bye bye.